Moving on, we have Joseph Francesco Bellissimo with his presentation.
Okay, welcome everyone to my project. My name is Joseph Bellissimo, and this is my pet project for UNERD 2020. And it's on rationally designed hydrolase variants for the degradation of polyethylene terephthalate. Okay, so as you all know, we are in the midst of a pandemic, but I might be referring to a pandemic that most of you probably aren't thinking of. The plastic pandemic has been a problem that has exploded over the last 100 years. And one of the things that is so alarming about this is that there seems to be a lack of interest to address it. And as we see, plastic pollution has been growing at a rate of over 100 million tons per year, and it's been having devastating effects on our ecosystems and on our human health. Okay, so on average, yearly production of plastics is around 8,300 million tons per year, and only 600 million tons of those are recycled. So this represents less than 10% of all the plastics produced per annum. And what it really shows is that there is a lack of all of this value. These plastics have all this value in them, and there's a lack of us kind of taking advantage of it and really extracting that value. So in terms of the composition of the plastic market, one of the plastics that I'm going to be focusing on today, called polyethylene terephthalate, also known as PET, only constitutes 7% of this global plastic production. But what makes it so special is that it constitutes 18.4% of all the recycled plastics. And so it's really considered the gold standard for recycling technology, because essentially it's kind of the easiest plastic to recycle. And so all of these different methods are being tested, like mechanical and chemical, to kind of see which works best. And it's really a good show of kind of the prowess of our recycling technology. So let's talk more about PET. So PET is synthesized from the monomers of ethylene glycol and purified terephthalic acid, and it's most commonly used in water bottles, containers, packaging, and textiles. And the reason PET is used for that is because it has some really favorable mechanical properties, such as it's quite flexible, it's very heat resistant, and it's quite strong and transparent. So now that we understand kind of that we have this plastic problem, and PET is kind of like the gold standard for what we can recycle. So what are the different types of recycling? So I kind of mentioned this earlier, but there's really there's 4 types, but there's really 3 that are of the most important. So there's mechanical recycling, called secondary. There's chemical recycling, which kind of what it does is it takes a plastic waste product and breaks it down back into its polymers or monomers. And then there's incineration, which is essentially kind of captures the energy from this plastic. So these are different ways to kind of extract value from this plastic. And currently, as you all know, probably mechanical is dominating the industry due to its low costs. Okay, but there is a problem with mechanical. And the major problem with mechanical recycling is that it's limited due to the loss of its favorable physical properties and its inability to deal with contamination. So what you see is, you can see in this graph in the top right-hand corner, that over time, as the recycling number increases, the Young's modulus also increases. So that really shows a loss of the favorable flexibility property of PET plastic. And then when you look at this table in the bottom, you can see a loss of this intrinsic viscosity value in this middle column in recycled plastics compared to virgin plastics. And so intrinsic viscosity is very important for different types of materials. So you want to maintain kind of the same level or a higher level of intrinsic viscosity when you recycle. Otherwise, you're doing something called downcycling. Okay. Now, so we kind of went over kind of the problems with mechanical recycling. So let's take now a look at chemical recycling. So one of the biggest issues, first of all, with incineration is that it's very costly, and there's also a large carbon footprint. So you can see kind of there's this represented in this top left graph, these pink energy bolts kind of show you kind of the energy input. And so this incineration approach is quite costly. There's so much energy input that's a lot of money being spent, and that means that the value we're extracting is less. And even industry leaders in chemical recycling via chemical catalysts still require a lot more energy than even mechanical recycling. So what this does is this really prices them out of the market. Chemical recyclers can't compete with mechanical recycling, and mechanical recycling can't compete with virgin PET plastic because it loses its properties over time. So what you're really seeing is that most of the industry doesn't want to use recycled plastic. They want to use virgin plastic because, again, as you see in this graph in the top right, it's cheaper and it's better quality. So we kind of talk about the failures of a mechanical approach and a chemical approach. So a new approach kind of comes up as a solution. So we have a biological solution is actually possible here. And we use enzymes as our method of kind of degrading these large plastic polymers into these small monomers that can be used to kind of close the loop and resynthesize those plastics at virgin level quality. And this can be done infinitely because, again, there's full depolymerization by these enzymes. And because enzymes are very cheap to produce and use in bioreactors, this solution is low cost. And since enzymes are very specific, it's resistant to contamination and impurities. So we talk about one enzyme that you can see here called this PETase enzyme, can break down this PET polymer into MET and BHET subunits, which then the secondary enzyme METase can break down into the monomers terephthalic acid and ethylene glycol, which can be used to close the loop and resynthesize virgin PET. Okay, so now let's kind of delve deeper into this solution. So this is the PETase enzyme that you can see on the left. And so there's essentially three enzymes to consider. This PETase enzyme that is known for depolymerizing PET, an LCC enzyme that does something very similar, and the METase enzyme that takes the this intermediate MET product from the PETase and LCC degradation and converts it into the monomers. So as you can see kind of this ligand docked in the PET active site. You can see there's different subsites in there. And then the kind of the mechanism by which this works is it uses a classic catalytic triad and a proton transfer mechanism, which is stabilized by this oxyanion hole, which kind of stabilizes, obviously, the acyl intermediate. So this is kind of how the enzyme is working and is able to actually break down this PET. So what it does is it really breaks down those ester bonds via this proton transfer mechanism. Okay, so let's actually get to the numbers. How feasible and what is required to get this to feasible? So currently the best enzyme to date has an average degradation rate of 19.35 grams per liter per hour. And so what this would represent is this represents 0.1 tons of PET degraded in 10 hours with a 5,168 liter bioreactor. And so the total annual cost to run a bioreactor is approximately $624,000 per year, which means that if you can recycle just upwards of 3,000 tons, you can be charging your PET at $200 per ton, which is actually the market for lower grade recycled PET. So that earlier graph had food grade, which is the highest level. So $200 per ton is for lower grade applications of PET. And so from these calculations, we see that we need our enzyme to be cost competitive to reach a level of 700 grams per liter per hour, which is 36 times faster than the current enzyme. Okay, so we clearly see that a protein engineering solution is needed. Now, there are a few options to this. There's a machine learning approach, which is a very powerful, and our colleagues on our team are actually using it. But some of the limitations of it is it requires a lot of data, it's quite hard to build, and it really only uses sequence information. Then you have your directed evolution approach, which is super random, requires a lot of lab work, which is completely infeasible this year, and is really costly. And then you have this rational design approach. So what is a rational design approach? So rational design approach kind of is using these different bioinformatic tools to make predictions about which residues you can mutate to kind of engineer your protein to improve. And so when we talk about protein improvements, we have this kind of fitness, this protein fitness landscape. And so what we want to do is we want to take our wild type enzyme and kind of get it to climb up to a local, or more often than not, global maximum. And so the way that we can do this is, again, as we talk, directed evolution, it climbs one step at a time. You can think of normal evolution. It only can go very slowly. Machine learning instead uses statistical sampling to kind of try and make guesses and start to kind of predict the function of how the protein fitness landscape works, and then it can use de novo synthesis to kind of generate the variant that most fits. And then a rational design approach is actually very interesting, and especially if you use it with multiple mutations, you can actually jump from different peaks so that you don't get stuck at a local maximum. You can jump from different peaks to eventually a global maxima. So it's a very powerful approach. Okay, so we kind of see, so the goal of our work is to improve this enzyme, and the way we want to do it is to increase its catalytic activity and its stability. So the way that we've done this is we've created a completely novel rational design pipeline here. And so what's super powerful about it is we believe that it takes advantage of kind of all these different factors and all these different bioinformatic techniques, and it can be done iteratively and somewhat generalizably. So when I refer to generalizably, the requirements are that it has to be to improve the catalytic activity and stability of a protein, and there needs to be some structural data already in the database and for that protein. And we believe that an iterative approach of this completely new method might be a way to get the global maxima of a protein and engineer it significantly. So let's break it down. So first, what we do is we have derived a Python script that allows for algorithmic searching of residues that are suitable for disulfide bond formations, which disulfide bonds, as you know, stabilize proteins. And this will generate testable mutants. So you can see right here, for the remainder of this presentation, I should mention that I'll be using Pedisan as an example, but we are done this as well with LCC and Medase in concert. So you can see here different locations that have been targeted for disulfide bond formation. And so we've also done this. Created a script that allows for algorithmic searching of residues that are outliers based on sequence and structural information. So we're kind of looking for hydrophobic residues, so residues that are out of place. So we use sequence and structural information using the PyMol visualization software to kind of see amino acids that are out of place and replace them with better ones. Okay, so we do that. So now we have all of these different targets for mutation. So these residues that are out of place and that can be improved, and these new disulfide bonds that can increase stability. So what we do next is that we use this technique called Rosetta Relax. And what it does is that it optimizes protein conformations and provides us with an accurate energy measure to rank our design. So it uses this Rosetta energy function to kind of optimize the conformation of your protein, and you can kind of use it to rank your variants and see how strong they are. And so you can see some of these results to your right. And just for reference, what is it called? And just for reference, the wild type is minus 740. Then we dock our protein to kind of see how it looks with the ligand, and then within it, and then finally we do some molecular dynamics simulations to kind of check to validate that our design was successful and to get approximations of the catalytic activity and stability of our protein. Okay, so sorry, what's happening? And so then we have a bunch of other methods to kind of generate residues for mutation and to validate them. But really the most important thing that we've done here is that we've designed a novel method for rational design intended for increasing catalytic activity. We have a set of enzyme variants with the potential to be used for large-scale PET degradation, and we have a large number of sequences that can be used as training and/or testing data for a future ML approach that lacks sequences. And so future directions is to validate these things, test if our pipeline is generalizable, and then to integrate our best variants into a microbial cases for a bioreactor. Any questions?
Thank you, Joseph. We ask the judges if they have any questions, please to turn on their mics.
Hello?
Yeah, Warren, your hand's up. Do you want to go first?
Sure. Yeah, Joseph, it's a very nice presentation. I very much enjoy how you sort of framed everything with respect of degrading plastic. So my question is really related to the machine learning algorithm that you're developing in terms of predicting, I guess, the most efficient enzyme system. And let's say your machine learning spits out an information that it has to be a specific conformation or specific amino acid structure. How do you actually propose to then put it to practice? How do you re-engineer your enzyme system based on the machine learning data?
Well, to be clear, we're actually not using machine learning here. We're using a kind of like a rational design approach that integrates different bioinformatic tools. So this isn't actually machine learning. So there's but like if I had these different mutations that I want to integrate, obviously you would just synthesize the sequence. And kind of the methods of testing validation is you can do this in silico via molecular dynamics, which shows the stability of your system and whether it actually makes sense. And you can obviously do testing in the lab with a fluorescent substrate. It's called p-nitrophenolbutyrate.
So would you make a library of different enzymes then to be able to test out?
Yeah, so what this method does is that it actually generates a large amount of different enzyme, different variants, each with different structural mutations to the structure, like your disulfide bonds, and then to the active site as well, using these different bioinformatic tools. And then you can kind of rank them based on your Rosetta energy scores, and then test like how many you want. So usually like the top 50 to 100 would be all you needed to test to see. From what we've seen in the literature and what we've seen in our work, 3-digit fold increases.
Great, thank you.
Yeah, no worries.
Unfortunately, we're running out of time, so we're going to be moving on to our next presentation. If any of you have any remaining questions for Joseph, please direct it towards the Questions for Presenters channel on MS Teams.